Sometimes in the history of engineering, physicists make their way into the story. Consider, for example, John Bardeen. You might not have heard of him, but Bardeen is the only person in all of history to win the Nobel Prize in Physics twice. He shared the prize once in 1956 and again in 1972. Both times he was involved in discoveries that made clever use of materials for electrical engineering. The first prize was for his work on the development of the transistor, and the second was for describing a way to allow certain materials to conduct electricity with no resistance, called superconductivity. Superconductivity is tricky to achieve, but it might allow us to transport electricity with nearly perfect efficiency in the future. Transistors, meanwhile, are electrical components that have already revolutionized society. They form the basis of all modern computing, and at their heart are semiconductors. As the name applies, semiconductors are in between materials that conduct electricity and materials that are totally non-conducting. A classic example would be silicon, which is so commonly used as a semiconductor that Silicon Valley was named after it. As we'll see, semiconductors have been transforming the face of technology for decades. On its own, silicon doesn't conduct electricity very well. It has no free charges like free electrons in it to carry a current. But you can alter the structure of silicon on an atomic level to change that. First, you replace a few of the atoms in a layer of silicon with phosphorus atoms. Those phosphorus atoms each carry one more electron than a silicon atom would have, which introduces more negatively charged electrons into the material. Those extra electrons aren't bound to any of the silicon atoms and are therefore free negative charges. For that reason, we call this an N-type semiconductor. N for negative. On the other hand, if you switch some of the silicon atoms with boron atoms, it creates a relative lack of electrons in the material. The boron atom has one less outer electron than the silicon atom it's replacing. The places where those electrons are absent are called holes. The lack of negative charge creates regions of free positive charge, so we call this arrangement a p-type semiconductor. Holes can move around and be transported in a material, just like the absence of water in a sealed container. A level, for example, forms a bubble whose location you can keep track of. You can think of holes as effectively positive charges that can be filled by the presence of an electron. When that happens, the space left behind by that electron creates a new hole. Now, on their own, those P and N-type semiconductors aren't all that exciting. Unlike pure silicon, which is an insulator, they'll be weakly conducting because they now have free charges moving around. But things get really interesting when you put them together. Like if you have both P and N-type conductors sandwiched together in a circuit. Normally, in electrical circuits, electrons flow from the negative terminal to the positive. Remember that the current is defined to flow in the opposite direction, so it travels from positive to negative. One thing you can do by sandwiching both types of semiconductors is to stop the current in a circuit from flowing altogether. If you put the N-type semiconductor on the positive terminal side and the P-type semiconductor on the negative terminal side, together they stop the current, even though on their own they'd each be weakly conductive. It works because each semiconductor's extra charges are the opposite of the terminal it's next to. All the negatively charged electrons in the N-type semiconductor are drawn towards the positive terminal of the circuit, and all the holes in the P-type semiconductor are drawn to the negative terminal of the cell. Since the effective charges are being pulled away from the area between the semiconductors, you end up with a gap between the two plates where charge can't be transported across, called a depleted region. Since there are no free charges to transport a current across that gap, an electrical current can't pass through it. So if you arrange P and N-type semiconductors this way around, you can stop a flow of current. But if you arrange them the other way around, with the P-type near the positive terminal and the N-type near the negative terminal, now the electrons and the holes are drawn towards each other. In this case, the extra electrons from the N-type fill the holes in the P-type, and the new holes spring up where the electrons used to be. This kind of a cascade can happen throughout the entire circuit, again and again, until you have electrons flowing much as before. In other words, in this arrangement, the current can now travel through where the N and P layers meet. The purpose of N and P-type semiconductors put together is the simplest form of what we call a diode, which is basically a one-way enforcer of electrical current. It allows current to flow in one direction, but stops it from flowing in the opposite direction. It just depends on how you insert the semiconductors relative to the terminals of your voltage supply, whether that's a battery, an electrical outlet, or something else. Being able to control the flow of a current can can be really useful. For example, you might have an alternating current or AC signal flowing through a circuit where the direction of the current changes back and forth. But many electrical components need a direct current or DC with a flow of current in only one direction. In the right arrangement, diodes can be used to convert a wavy AC current into nice simple DC current. The flow of charge in the DC part of the current always goes the same way, and the positive and negative ends of the output remain the same, like a battery. So diodes are handy for controlling the direction of a current, but you can do even more if you put 3 semiconductors together in a sandwich. You have 2 options for this type of sandwich, PNP or NPN. In both cases, the middle layer effectively creates a diode with each of the outer layers, with each diode allowing current to flow in the opposite direction. This may not sound terribly useful because together the 3 semiconductor layers are restricting flow both ways, unless that is, you add a second current. Let's say you have an NPN sandwich connected to a battery. The current can't flow through it because you have a positive terminal hooked up to an N layer. The electrons in that layer will be attracted to the positive terminal, while the holes in the P layer are attracted to the other N layer. So you end up with a depleted region between them, and the current is going nowhere. But here's the incredible thing. If you apply just a small current that flows from the middle plate to the N layer on the same side as the first battery's negative terminal, the electrons moving into the P layer fill the depleted region between it and the other N layer. So that gap the electrons couldn't cross before disappears, and the original larger current is free to flow across the whole sandwich. In other words, you've created an electrical switch, a sort of gateway that requires just a tiny current to control the flow of a larger current, and it works for PNP arrangements too. This arrangement of semiconductors that might seem so functionless at first is a transistor, and the fact that it allows you to control how current flows in a circuit makes it one of the most important components of the electronic age. Since transistors use smaller currents to influence the on or off states of the larger currents flowing through the wire, they form the basis of the binary system of ones and zeros that computers rely on. All the marvels of computers and computer chips, including your ability to watch this video, depend on semiconductors and the transistors we make from them. So that's how materials like semiconductors can direct the flow of electrical power. But semiconductors can be used to generate electrical currents too. And that ability has allowed us to take advantage of an incredibly useful source of clean, renewable energy. To see how this works, let's go back to a simpler diode set up with a P-type and N-type semiconductor put together. This time, you don't connect the 2 sides to a power supply. Instead, you attach it to a device you want to power, like a small electrical motor. Remember, the N-type will have an abundance of free negative charges, and the P-type will have an abundance of free holes. There's no voltage being applied across the junction between the 2 types, so the electrons of the N-type will naturally fill the holes in the P-type. This creates a depleted region at the interface between the 2 semiconductors. There are no free charges because the electrons become weakly bound to atoms when they fill the holes that were in the P-type. The N-type has a small region with some positively charged atoms from the absence of those electrons, while the P-type has a small region with some negative charge from those extra electrons it picked up. These opposite charges set up an electric field across the gap. If there were any free electrons in this field, they'd be driven away from the negatively charged region in the P-type towards the positive region set up in the N-type. So that's our setup. Now, how do you get energy from this? On its own, it's not going to do an awful lot. But electrons in a material can respond to light. When light hits them, the electrons interact with the light and can even absorb some of its energy. If the bound electrons in the P-type absorb energy from the light shining on the material, they can get just enough energy to stop being bound to atoms and become free charges. Remember that the charges across the gap set up an electric field. Electric fields apply a force to free electric charges. So an electron freed from the extra energy it got from the light is now driven by that electric field into the N-type. That leaves a hole in the P-type waiting to be filled. But the electrons can't flow back against the electric field. The forces push it the other way around. Instead, the N-type's extra electron will flow all the way around the circuit through the device, delivering electrical power. That's a solar cell. With the right arrangement of semiconductors, it allows you to generate electricity from light. These kinds of cells are exactly what form the basis of solar panels. With semiconductors and silicon in particular, you can create electrical power from sunlight, and I think you'll agree that's a pretty bright idea. In this episode, we looked at silicon and how introducing small amounts of other elements allow silicon layers to conduct currents, turning them into semiconductors. We saw how putting 2 different types, N and P semiconductors together, gave us electrical components like diodes, transistors, and solar cells. Next on our tour of materials engineering, we'll be going super tiny as we explore the world of nanomaterials. Crash Course Engineering is produced in association with PBS Digital Studios. If you want to keep exploring the world around us, check out Reactions. It's a show that uncovers the chemistry all around us and answers the burning questions you didn't know were chemical. From whether gum really stays in your stomach to why bacon smells so good. Check out Reactions and subscribe at the link below. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.